something you want to see. All right, so for the sake of time, let's do a quick. I'll go ahead and lead us in a Hail Mary in the name of the Father and the Son and the Holy Spirit. Amen. Hail Mary, full of grace, the Lord is with thee. Blessed art thou among women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and at the hour of our death. Amen. All right, gentlemen. So I'll even read you the mustard seed because I always think they're important. Today's a quick one. If you sow thistles, you will not reap corn. Pretty to the point. So sow good seeds, good mustard seeds. All right. So we left off last class discussing the terminology, what equating a water circuit with the electrical circuit. So my objective for you today is to just give you some terms, basic terms, so you can move forward. And then for homework this weekend, you can see listed up here on my whiteboard, I have a lab that is online that I actually hope that you guys really get a lot out of. It's pretty cool. It's from the University of Colorado, has really interactive, great interactive physics labs. You probably use it in chemistry and biology already. But they have a really good circuits lab that I want to walk you through and explain how you're going to do this. So the purpose of your equipment, you can use it and build, and that's what's written in your lab. But I don't want that to be the stressful part. Like if you're not getting it to work the same as what you see on the computer, then, you know, I'll have to give you feedback on that. But I want you to play with the equipment. I want you to cut apart the lights and see all of that. But for priority, let me just finish where we were last time in talking about the water circuit, okay? And what are some of these terms? I think we got through the whole thing, right? So if I go back, let's see. Okay, similar to water. Okay, I got something different for you guys today. I'm gonna move this down. Found in my closet, one of my favorite all-time toys that we had for the kids. Did any of you guys have one of these things called Marble Works? Where you take a marble and you drop it in. So let me move that back a little bit further. Right? And you drop it in and it goes down. And as it falls down, right, it spins. So very similar to what we have with our water circuit. So the reason I wanted to pull this out was, here's the scenario. Here's these marbles. We often think of electrons as little circles, little masses like that. We really don't know what they are, what they look like, if they're made up of anything, but we often look at them as these little things. They naturally want to go somewhere. So we were talking last time about water, naturally wanted to go to the ground, right? So the fact that this is just going to naturally fall when I release it, that's where it's in its lowest energy state. So in this low energy state, that's where it likes to be. I'm going to have to do some work to lift it up, right? So if I do work to lift this up and then I drop it in here, the fact that it wants to fall down, I can use that. So if I make it follow a particular path, when it falls, then I can get something out of it, like this wheel spinning right here. So I can lift this up, and when I release it, I get something useful out of it, which is that wheel spinning as it falls down. And I can reuse it, right? Send it back up, drop it, use that energy to cause the wheel to spin. So that's the visual that I wanted you guys to have as we talked about water last time. But it's the same thing with electricity. If I have a whole bunch of them, right, I'm giving them all the same amount of energy. How many I put in here will make a difference on how long that wheel spins, right? So the more I put in there, the more or longer it's going to be able to spin. But each one of these individual things have the same amount of energy that I just lifted them through. That makes sense? It's our favorite toy. I'm never going to get rid of this. Never get rid of Hot Wheels, Legos, and my Marbles Works. That's my role in the house. All right, so let's go back and draw this. And what does this have to do with electricity? Okay, so I want you to think of those marbles as the electrons, right? So instead of our water cycle, since I just demonstrated, I'm going to go back and put up our electrical circuit. So the purpose of that battery, again, is to take the electrons and literally pump them where they don't want to be. And that's where they don't want to be, is separated from the protons. So electrons and protons like to be together, and the world likes to be neutral, just like water likes to be down and things are going to fall. So inside that battery, again, you have positives and you have negatives. The battery acts as a pump, right? That pump, what I want you to know today, is our voltage. So a voltage raises the electric potential energy. Of the electrons. Okay, so it's going to raise the potential energy of those electrons. When it raises them, and technically it's doing that again because they're separated, the voltage source. So the definition of a volt is a joule per coulomb. How much energy are you giving each and every electron? So that marble that I was lifting, I was doing work on it to lift it up and give it energy. So the energy came from me, but here the energy, we had to do something to separate those. So that's the energy source. We're going to give each one of these electrons energy. The wires serve the purpose of taking those electrons somewhere, right? And what we're going to do in our light bulb, what you may or may not know about the light bulb, is you must enter the light bulb and go through a filament and then exit the light bulb at the bottom. So a complete circuit, you must have a complete path. There can be no gaps involved there. And then you're going to send them back, right? And as the electrons fall, they go back to where they want to go. So the difference with electricity is I'm going to take them from the negative and send them back to the positive. And this is why your batteries die out, because you've now mixed them. It's become neutral. So you are no longer putting those electrons at a higher energy state. So again, the wires, right? The purpose of the wires is to lead the electrons where you want them. Right? And the light bulb uses the energy and changes it to light. Okay, that's what we're going to do in a light bulb. Similar to the marble. So instead of me getting that spinning motion, I'm going to get light out of it. I could put a fan in there and get a spinning motion. I could put a speaker in and get sound. You're simply going to take this electrical energy that you're storing in the battery, change it to something different that you can use. Okay, so some words that I want you to just be familiar with so that when we are communicating, they make sense. Okay, we said last time we have a circuit. That is simply a pathway. If I say we have a closed circuit, this is a pathway with no gaps. Okay, there are no openings. So here's the neat thing about electricity, and here's the frustrating thing when you're building. If there is an opening anywhere, so obviously if there's something here, the electrons can't go across. But even if there's an opening over here, it's not like the electrons are going to go through the light and hang out here. That would actually happen with water. That would happen with the marbles. Even if I have a break in that circuit, that stuff will still flow. It just will not go to where I want it to go. In this case, with electricity, if you have any opening anywhere, nothing will flow. So for electricity to flow, you must have a closed circuit, right? So that's going to have to be closed. If we want to make it open and shut it off, we call that an open circuit. In an open circuit, there are gaps. Okay. So that's something that is really, really important in electricity that has been designed is a switch. I don't want to have to constantly disconnect these. So I want to put something in there, which is simply a switch. And a switch is simply a device that easily allows me to make an open and a closed circuit. And those switches are very important in your rooms in your house, of course. As you walk in, you don't want to have to turn on the light bulb by screwing it in. You want to just flip the switch on. So switch creates an open and closed circuit. A word that I'm sure you often used or heard is a short circuit. Okay? So in a short circuit, what you do is there is a bypass of a direct path from positive to negative. If you create a short circuit, it's like a free-for-all. You just connect the positive and negative without the electrons having to do any work. So when the electrons come out and they go through here, they want to get over there, but by making them go a certain path, we're using that energy. If I connect without connecting through that battery or that light bulb, and I just connect directly positive and negative, they're going to fly because you're giving them a free pass to be able to get to where they want to go without having to do any work. When you get that, the wires will get hot, your battery will get hot. So if you feel heat, something's wrong. So number one rule when you are building these circuits, if your wires are getting hot or your batteries are getting hot, you must have a connection in there that's directly connecting your positives and negatives. And be careful of that. Notice, I never go back to the negative, right? I go back to the battery, but not the same part of the battery. You leave the negative, you go back to positive, or vice versa. So going back to the battery does not mean you go back to where you started. Okay? So some words that we have there. All right, real quick. Just a quick view there. Everybody good? Thumbs up. Brock, you better be paying attention. You don't get any of my time later. Everybody good? Ben, you still with me? Brendan? All right. All right, here we go. Just a few more terms and symbols that I want you to be aware of. Okay, voltage. Letter V, right, in our symbols, it is the pump, right? Measured in units of volts. So it's the energy. All right, that's all I need you to know for now. I'd love to elaborate more on that, but that will get you through. Current is a capital I, and it is measured in units of amps. Okay, capital I measured in units of amps. It is the number of electrons flowing per second. And that also matters on the cross-sectional area of the wires. With your Christmas lights, you'll notice the copper wire is very, very thin, but there's a lot of them. House wire, very, very thick. So the amount of current that can flow through, no different than the pipes. You need more water, you'd have a bigger pipe, right? Voltage, current, and resistance. Capital R, measured in units of ohms. Okay, this is the opposition to the flow of electrons. Okay, this uses the energy. Okay, your resistance in the circuit is going to use up that energy that you are sending the electrons through. So over here, the resistance would be my light bulb. The voltage source, of course, would be the battery. The wires have no resistance, but they are carrying the current. So the current is flowing everywhere. So the current, I want you to think of as my handful of marbles, right? So I have all these marbles. That would be the current. However many marbles I have in my hand, that would be the current that I would describe. How high I lift these would be the voltage. So the higher I lift them, the more energy each one of the marbles gets. But I could lift a lot of marbles not very high and make the wheel spin, or I could lift a few marbles higher, giving them more energy, making the wheel spin, or I can lift a lot of marbles very high. So how high I lift them would be considered your voltage, the energy you give, the amount of these marbles would be your current. How hard it is for these marbles to go through that path would be the resistance. And as they go through, they use up their energy to pass through. Okay? All right, how are we doing with those terms? Any questions? I'm sure you've heard most of those before, but that is your basics behind electricity. So now what we want to do is, well, how do we use those? And I want you to build with these. So something I want you to try this weekend is what all of the electrical engineers somewhere along the line had to come up with neat ways to connect things. So your challenge is to do just that. What's an easy way to connect? It's hard to keep twisting wires. So extra credit to the person who can design a really cool switch, who can design a neat way to connect things. So that's what I'm looking for. I really want you guys to get creative in how you're doing with this. So the Christmas lights and everything are just something we could all get without going shopping, and it's going to serve our purpose and allow you to kind of investigate with some electricity. So before I continue on, let me show you some things that you're going to do with your wires. Okay. All right, so your Christmas lights. All right, so when you get these, I got so much stuff in here. All right, let me go back and go back to here. All right, so Brenda and some of you have started taking these apart, but remember you're going to take them apart. You don't want to cut them all at once like this, because what you're doing is then you're wasting the wire that we're going to want to have for connecting wires. So with your Christmas lights, so you can start cutting one of them, but as you twist those apart, so you can see how I'm untwisting it, I'm left with all of this wire that has no lights on it. That's going to be good connecting wire. These lights, I'm going to cut them right in the middle, right? So you can, if you have wire strippers, that's nice, but if not, scissors work just as well. So you take that wire and you barely cut through it. Okay, and you can feel it when you get to the wire. And once I cut through, I can just pull that off. And what I'm left with there is my copper that's right underneath there. So if you take that copper, if you cut it too far, you'll end up with only like one or two little hair-like things. You want as much of that wire as you can, and you can twist it and it'll seem like a solid piece of wire. I'm trying to hold it so you can see it as well. Okay, you're going to do that on both sides. You don't need too many lights. I mean, depending on what you want to build. All right, this extra wire, you can then cut to whatever length you want when we begin building our project. And same thing with that wire. So now I have a nice piece of wire and I can strip the ends of it. You must take off the insulation, have any connection. And then I can just pull that off and there's my copper wire there. So my question, if you can come up with a neat way to not constantly have to twist these wires together to reconnect, then that's cool, maybe with aluminum foil. Another neat thing, something you might have, I listed paper clips. So paper clips will work well for making a switch when you are building. So this is not the house project, but maybe on a piece of paper or something like that. You want to connect wires to your battery. You can tape your battery down so then you can connect things. And then the hardest thing to connect, so you can see my light has been stripped, my wires, is then making a switch. So one thing you can do with some paper clips, all right, is you can make a very simple switch, and that switch, somehow you have to connect little brass nails, another paper clip, something, so that you have a knife almost swinging back and forth, and that will be your switch. Okay, so those are some ideas of how you're going to cut that apart and build with to move forward. Okay, so getting back, anybody have any questions on how you can cut up the lights and stuff? Everybody good? It can get frustrating when you're cutting with those scissors because you quickly cut through. All right, so to build circuits. So your lab this weekend is you're going to build me 8 circuits virtually online, and then I want you to practice building those with your supplies. So this is not, you're not using your shoebox to build the room. This is you just kind of practicing. So of course I can't see your circuits that you build. If you want to take a picture of one, You don't have to build them. I'm just saying if, it is neat. So if you want to investigate that a little bit more and build. So the next thing we have to do is, instead of drawing pictures like this, we want to draw diagrams. So the next thing I'm going to share with you guys, I'm going to have to pull it back up since my computer stopped. I'm going to do a shared screen here of your lab and show you what we're going to do. So it's pretty, I wrote it up pretty detailed so that you should be able to follow it without too much trouble. Let's see. Sorry for your wait here. I had it pulled up until my computer shut off. Okay. Okay, you guys all good? No questions? Let's go down here to share my screen. Okay, so what you will find on Blackbaud right now is this file that you can pull up. Okay, it says you have two parts. So you have part one, circuit construction, and then you have part two down here as you scroll down. So there's a part two. You are not doing part two, just part one. We'll do part two next week, so if you want to get a head start. Then it looks like you have nothing there, but keep scrolling down, and this is an important page. Okay, so as you get to the bottom, everybody take a look at that now. So here's our circuit diagram symbols, all right? So instead of using a battery or drawing the battery as it is, this is our symbol for a battery. Instead of a wire, you just draw a straight line, resistor, a light bulb, a junction where two wires come together, capacitors. If we have time, I'd love to teach you about capacitors. And then there's our symbol for a switch, just like it looks. So instead of drawing these actual things, when we draw circuits, we draw circuit diagrams. If you scroll further down, you'll need this page. Here are 8 different circuits that you're going to build in this lab. All right. So when you build those, you are then at the same time going to, let me give you a new share, pull up the lab data sheet. Okay. So you're going to pull this file up. That looks like this. Okay. So this is where you're going to record your information. So the easiest thing to do is to copy and paste that circuit right into here, which I had done earlier. And let me do, I know you have that file, but I'm going to go back and I'm going to say, okay, if we want to build circuit number 3, okay, so I'm going to start with circuit number 3. And let's see, you guys are in here, right? So if I scroll down here to circuit number 3, sorry, hold on a second. Copy this. What I would do is go into my lab and I'm just going to put circuit number 3 in there. So I snipped it and copied it. So there's circuit number 3. So for each one of these boxes, you are going to put in each one of those circuits. So I want you to hand draw those in, or you can cut and paste just like I did right here, and you'll put those into your lab. Okay. What you are going to do is build these circuits, and you're going to tell me how much voltage and current goes through each one of these bulbs. So what I want to record on here is I'm going to record a VT, which is a total voltage. I'm going to record a voltage across bulb 1, and I'm going to record a voltage across bulb 2. Okay. And then I'm going to write down what is the current, capital I, total, which means the battery. And then I'm going to record the current through bulb 1. And then I'm going to record the current through bulb 2. Okay, so that's how I'm setting up my data sheet. All right, I know you probably have questions on that. Let's go back. Okay, is everybody following that? So you're going to have 2 sheets on Blackbaud. They're already there. The circuit, the lab directions, and then your data sheet. So let's go back to the lab directions. Okay, let's see here. All right, that's our data sheet. No. Okay, hold on. This is one we want. All right, so that's at the end of that lab write-up. At the beginning are all your directions, right? So it tells you exactly what to do, step by step. So here's what you're going to do. Here's the important part. You're going to go to this website. So I'm going to copy that, and I'm going to go to that website. Okay, now, let me share. I'm going to share my screen with you. Okay, so when you go to the website, this is what you're going to see. Okay, let me just verify you guys are all seeing, it says Circuit Construction Lab. Is everybody seeing that on your screen? Okay, so you're going to go here, and again, this is pretty cool. So here's where you get the build. If you need to watch, you can do this, but you're going to choose the lab. All right, so when I choose the lab, it's going to pull that up, and here's my workspace. Over here on the left, I have all these supplies. On the right, I have all this information here. I have meters and so on. So what I'm going to do is I'm going to build, if you remember what circuit number 3 looked like, it had 6 volts. So I'm going to pull in my battery, twist it around. That's the direction I want to go. Nope, I think I want to go this way. That'll matter on the demonstration. All right, so there's my battery. And then I can pull in wires. So here comes wire number 1. When I put it in, I can take one end to swing it around. I can make it longer or shorter. Okay, take wire number 2, bring that over, wire number 3. So you can just keep bringing in wires. And in circuit number 3, it had 2 switches and 2 light bulbs that were all connected together. So I'll pull in my light bulb, right, swing this around. Be careful when you're moving these. As I said, the light bulb mustn't be connected at 2 different places, and make sure that you're not bypassing that light bulb. So I'm going to bring in another switch. Right. Another light bulb. Might run out of room here. And then another wire. And it doesn't have to necessarily look exactly how you build it, how it looks on the diagram, but it makes sense to build it that way. All right, so there's our circuit. So if I go back over here and I go back to my diagrams, there's circuit number 3. I have a battery and 2 light bulbs. Okay, so when I go back to my circuit here, my job now is to make sure this is 6 volts. So if I click on the battery, I can change the voltage. And actually, I don't know if I can go as low as 6. You can actually type in your number right here, I think, maybe not. All right, so there we go, it goes up by 0.5. So I have that at 6 volts. That's what what it's supposed to look like. I'm going to close each one of these. So just by clicking on it, I close. And I recognize, oh, closing my one switch did not turn on my light bulbs. I need to have both switches turned on. And you can see here, the electrons begin moving. They're not moving very fast. The speed of these electrons are relevant to the voltage, okay? So what I want to do now is I want to measure voltage and current. How many, and this is physically what's really happening inside your wires. These electrons are moving. Of course, if I increase my voltage, right, the bulbs will get brighter, the electrons will move faster, and that's because I'm giving them more energy, right? So the question that I want you to try to figure out in this lab is, what effect is there on voltage, number of light bulbs in the circuit, and so on? So I'm going to dial this back down to 6 to get us to where we want to be. And then I want to take measurements. Here's my voltmeter. So with the voltmeter, to measure voltage, I'm going to touch across these 2 points where the bulb is. Notice I get a negative. That's not a big deal. I have a red probe and a black probe. Black should be on the negative side, which should be this side first because the way my battery is set up. Red is on the positive side. So once that is connected properly, I will get my voltage, and it's 3 volts. I'm going to measure the voltage of my other bulb, and it's 3 volts. So I'm going to go back to my data sheet, and I'm going to type in my total voltage was 6 volts. V1 was 3 volts, and V2 was 3 volts, right? Go back to my lab. Now I want to measure current. So I'm going to put my voltage away. And current, this is an easy meter. A real ammeter does not measure like this, but for this lab, if I want to measure the current in bulb 1, it's 0.3 amps. Bulb 2, 0.3 amps. Coming out of the battery, 0.3 amps. I should be no surprise there, because obviously the number of electrons that come out of here must go through here, and they must also go through here. So all of them then have a current of 0.3 amps. So I'm going to come back here and say 0.3 amps. 0.3 amps. 0.3 amps. And then I'm done. Make sure you're measuring your totals. Notice, if I go back to the lab sheet, you are building 8 different labs. So 8 different circuits. These are all different, especially 5 through 8. These are a little trickier. Your measurements aren't that simple. These 1 through 4 are simple circuits that should just become very familiar and easy for you to do. But the other circuits are not as easy, 5, 6, 7, and 8. So please pay attention to your measurements on those. All right. Let's see. Let's go back to the lab over here. I do want to show you that this ammeter is a proper ammeter, which is to truly, if you were to, when you buy a house, everybody should have a multimeter in their toolbox. And if I click on this, if I right click on it, I can cut it out, or if I just click on it, then if I hit this delete, it'll take that away. And the reason I want to do that is that's how you would put this meter into place. So I'd cut that and swing this meter around, and it measures the current right there. So current really should be measured by disconnecting wires, and that's what's written up in your lab sheet. So in your lab sheet, again, if I go back to this, I have pictures, directions showing you exactly what you need to do, okay? So this is what you're seeing on the computer. This is what you're drawing in your data table, what you would see, okay? And just some notes on taking the measurements of current, taking the measurements of voltage, okay? How do you change battery voltage? You can also, when we get to phase 2, circuit number 2, if we do that next week, oops, nope, I want to go here. Okay, if I go back up here and I hit values, it'll show you the values of resistance. So I want you to make a note of that. The resistance of each bulb, we're not going to change that, is 10 ohms. So that's going to be true through all of the labs. Okay, you're not going to change. If I click on the bulb, just like the battery, I can change its resistance. So if I increase my resistance, notice the electrons go slower and slower because it's harder to get through those. The brightness of the bulb gets less and less. So next week, we're going to talk more about the relationship between voltage, current, and resistance, and why is there exactly 0.3 amps coming through there. So if I put that back up to the 10 that it was, get back to the numbers that we had. All right, so why is that 0.3, 6 volts? Why did they split that up evenly as far as the voltage, but they have the same current? Those are the trends that I want you to see. If you go back to circuits, let's look at our more complicated circuits. Okay, if we go down here to circuits 5, 6, 7, and 8, notice you have branches to these circuits, okay? So going back to your lab, when you build those, you can bring a wire and connect it at the same place. So then I'm going to have a branch. So some current can go through here, and then some of it, when this is connected, notice that nothing's going through there, then no current's going to flow because you have an open circuit. All right, real quick, a short circuit is me bypassing all of that and directly going to the negative. What happens? Everything stops going through those, and all of the electrons say, oh, it's a freebie. We don't have to do any work. Notice that the battery is on fire. That is your short circuit. So definitely don't want that. All right. So if that's in your building. It's hard to do that on the computer, but that will happen in the construction. All right, gentlemen. I want you to have some fun with this. So the goal is, with your equipment, can you like tape down your wires and everything and actually build circuit number 3? Now I will tell you that as we continue to screen share here, if you are using AA, AAA, or any battery other than a 9-volt, you're going to have to connect your batteries together. When you connect your batteries together for your equipment, make sure you're connecting positive and negative. Sometimes it helps to slip a piece of aluminum foil in between and then just tape them together really tight. But they must be positive and negative. If you are using a 9-volt battery, more than likely, if you leave it on for too long, you will blow out your light bulbs. It's too high of a voltage and it'll burn out your light bulbs. So be careful of that. It comes on long enough to turn them on and then quickly shut them off so you don't blow out your light bulbs. But if they stay on for too long, they might burn out. Okay? So I'm going to unmute you guys. Any questions, comments? Nothing?
No, ma'am.
All right. So on the computer, you're to build those 8 circuits. You're to complete that lab data sheet. You are going to turn in the lab data sheet for me by Monday before class. Okay? Next week, then we'll talk about what you saw in each one of those circuits and then start your actual construction. So if you want, on the side, you can actually build the circuits and practice with that and do that. Okay? All right. Nobody has any questions? Everybody's got supplies? All right. I won't see you guys until Monday, but my plan is that on Friday, I am going to go set up some stuff at Benedictine. So if you want to come and get some more supplies for your project, which is little motors. I see right now, Matthew, you have a nice ceiling fan. Frankie, a ceiling fan in front of your head. So if you want to put a ceiling fan in your model, Brock, everybody has a ceiling fan. So somehow I need to get you all some motors. And honestly, Brock, I know this is the case for you. Anybody who's closer to me than you are at Benedictine, so I'm near Lee Davis High School.
And close.
You can come get it from me as opposed to going all the way to Benedictine. So
I'll deliver it for extra credit.
You'll deliver?
Yeah, for extra credit.
I don't know if I want that. Well, the goal is I'm going to lay them out and they're going to sit for 24 hours. So that's the rule on, does the virus stay on surfaces? 24 hours, they say. So just in case I'm carrying it and I touch something, I don't want you coming touch it. So I'm gonna lay it out. And then it'll be laying out for you. So I asked you the same thing. If you come and get little mini motors to build ceiling fans in your model home, that you're not like putting your hands on over everybody's stuff. So anyway, Brendan, I hope you have a great weekend. You gonna smile?
You too.
I will. All right. Email me if you have questions. Everybody try that lab maybe today or tomorrow and make sure that you can get online. You might have to download Java or something like that, but it's all free. You should not be paying for any software to do that lab. It's all free. Okay? So click on the website is in the lab write-up, and that's it.
Have a great day.
All right. See you all later. Bye.
Wait, ma'am, I have a question.
Yes.